All right, I think we can get started. Welcome everyone to the CGD seminar this week. I'm happy to introduce Dr. Jerry Meehl as our speaker. Jerry's a senior scientist in CGD and heads the climate change research section. He's also chief scientist of the Cooperative Agreement to Analyze Variability, Change, and Predictability in the Earth System, or CATALYST, which is a project that involves NCAR and the Department of Energy. Jerry received his bachelor's in atmospheric science and his PhD in climate dynamics, both from the University of Colorado Boulder. His research interests include identifying effects on global climate from anthropogenic and natural forcings, quantifying changes in climate extremes, and understanding the interplay between internally generated climate variability and the response to external forcings, particularly in the context of understanding decadal climate variability. He has participated as an author in the first 5 IPCC assessments and also involved with the World Climate Research Program, or WCRP, working group on coupled models. He recently received the UCAR Distinguished Achievement Award in 2019 and for, quote, achieving high impact groundbreaking research on understanding the interplay between naturally occurring climate variability and the long-term climate change from increasing human-produced greenhouse gases. Today, he will speak about the role of interannual ENSO events in decadal timescale transitions of the interdecadal Pacific Oscillation. Jerry, the floor is yours.
Okay, thanks for that introduction, Katie. And the actual underlying topic of this talk today is timescale interaction. And so this is the idea that something happening on one time scale can affect something happening on another time scale. And in this case, the timescales of interaction are, we're going to look at the interannual timescale of El Nino Southern Oscillation events in affecting the decadal timescale transitions involved with something called the interdecadal Pacific Oscillation, which is a decadal timescale phenomenon. So I want to acknowledge collaborators on this work, Haiyan Teng, who's now at PNNL, Antonetta, who's at CU Series and NOAA, and Aishu, who is also at NCAR. And this paper is now in press in Climate Dynamics. So the real motivation for this is decadal climate prediction. And the goal is to try to make skillful decadal climate predictions. In other words, predict the time evolution of climate over the next several years to 10 years or something like that. And you'd hope that there are some decadal timescale processes with mechanisms that arise from coupled processes in the climate system. And because these are slow, it's usually assumed that the ocean is going to play a major role in these kinds of mechanisms. And then for the decadal climate prediction problem, if you initialize these mechanisms properly into the initial state that you start the prediction from, that then you would get these kind of mechanisms going, and they would kind of proceed over the next 3 to 5 to 7 years to give you skill just from the internal processes that are producing these kinds of climate patterns. That's the hope, that we'd be able to have some skill provided by these kinds of mechanisms. So when you look at the literature, there's oftentimes a couple of mechanisms or a couple of processes that people are hoping could provide this kind of skill from internal variability. For the Atlantic, the AMO, Atlantic Multi-Decadal Oscillation, which is now more generically the AMV, has this kind of pattern where in its positive phase, the sea surface temperatures over most of the North Atlantic are positive. And you can get a time series of this, of the AMO. In this case, this is the Trend-Berthon-Shea index, going from positive to negative phase. Of course, this is low pass filtered and detrended. And you can see there's maybe 2.5 cycles that we've got captured in the observational record in one way or another. For the Pacific, the IPO or the PDO are both very similar. Both are now kind of generically referred to as Pacific decadal variability. And of course, there's others, Pacific meridional modes and NPGO, North Pacific Gyre Oscillation, but a lot of the literature is looking at IPO and PDO, and that's what we're going to be focusing on today. And the IPO, I'm going to be referring to as the IPO because the IPO is defined as usually some kind of UF pattern of sea surface temperatures over the whole Pacific basin. In this case, this is the second EOF of observed sea surface temperatures, low pass filtered, and you get this kind of characteristic pattern with this kind of broad wedge-shaped sea surface temperature anomalies of one sign that extend all the way across the Pacific, all the way over here to the Western Pacific, opposite sign anomalies to the Northwest and Southwest. Has this kind of characteristic time scale. And again, there's only a couple of cycles that we've got in the observational record. So those are the candidates, possible candidates. And there's at least a couple of possibilities for how we understand these phenomena. One is this kind of null hypothesis view that they actually do not exist as internal process-driven phenomena, but they are artifacts that arise for other reasons. And this could be aerosol forcing, anthropogenic aerosol forcing that has a time evolution that seems to coincide with the time series of the EMO for AMV, and that there could be for the Pacific, for the PDV or the IPO, there could just be random groupings of El Nino and La Nina events, such that when you low pass filter it, you get this kind of El Nino, La Nina-like pattern that occurs on these kind of slower time scales. Scott Power and Rob Coleman had a paper where they were kind of proposing that as a possibility. There's other papers that have been done in the same kind of theme. Some of them are amplitude modulation of El Nino and La Nina. So maybe these phenomena don't exist at all. These decadal timescale phenomena don't exist. They arise from other things that are going on in the system. But the other viewpoint, which is possibly the more optimistic for decadal climate prediction, is that they do have mechanisms and there are internal processes that generate them. And this could provide prudential predictability for initialized predictions. One of the things that have been looked at for the AMV is the AMOC, Atlantic Meridional Overturning Circulation, that if you could kind of predict that slow evolution of the AMOC, the overturning in the Atlantic, that gives you some information on the sea surface temperatures associated with it on decadal timescales. And there's been some candidate mechanisms for low frequency tropical mid-latitude, air-sea interaction for PDV. ISU and I proposed one in 2006, which was kind of confirmed with more recent data by Farnetti et al. In 2014. So anyway, there's at least two ways of looking at this, and we're going to look at it from the second point of view here, that there are some internal processes that produce this internal variability that we, if captured in an initialized prediction, can give us some skill as this internal variability evolves over the next 3 to 5 to 7 years or so. So why do we care about this? And because we're always looking at these phenomena in terms of sea surface temperatures a lot of times. So when I was showing you that pattern of the IPO, that's obviously defined for the Pacific Basin, the ocean areas of the Pacific. AMO is obviously the Atlantic Ocean areas. But the idea is that because the sea surface temperatures drive teleconnections to other parts of the world, that if you could capture the prediction of say something like the IPO, the pattern of the IPO in the Pacific, that could give you some insight into what could be happening with precipitation, in this case, in other areas of the world. This is the IPO index correlated with low pass filtered observed precipitation for the 20th century. So when the IPO is in its positive phase, when the tropical Pacific SSTs are above normal, you tend to get above normal precipitation over the southwestern part of North America, below normal precipitation over Eastern Australia, area averaged over South Asia, below normal precipitation typically over South Asia, below normal precipitation over parts of Africa. And so because of the teleconnections that are driven from especially from the tropics in these ocean basins, you maybe get some information on not only mean, but extreme precipitation and heat, mean and extreme heat in these other areas over land. And there's some indication that if you actually could initialize the IPO in the proper phase, or actually predict it, that you could get some information over and above what you'd get just from the external forcing. And this is from a paper by Boardbar et al. That appeared a couple of years ago in Nature Communications, and they were looking at several climate models. This is an example from the Korean model, that if they initialized some predictions within a neutral state of the IPO and ran the model forward for 20 years, you can see it's warming up everywhere just from the external forcing, but and you get some kind of warming of 0.21 degrees C per decade. But if you initialize the model when the IPO is in its negative phase, you can see there's more dark red colors here, which means you're getting more warming over more regions of the globe. And the trend, the global average temperature trend, is 0.31 degrees C per decade. If you initialize the model in the IPO positive initial state, you're seeing less dark red colors here, so you're getting less warming over most areas of the globe. And in fact, the trend in global average temperatures is down to 0.03 degrees C per decade, which is an order of magnitude less than it was if you initialized the model in the IPO negative state. So there's some indication that you could get some skill if you could predict something like the IPO in things at least like temperature over decadal timescales. Now, when it comes down to mechanisms, there's a lot of mechanisms, or at least a couple of mechanisms that have been involved with tropical mid-latitude interaction. There's other mechanisms for the PDO that involve processes that are occurring mainly in the North Pacific. This is just an example from our paper in 2006. Aishu and I put this paper together where we were saying that looked like in the model we were looking at the time that if the IPO was in its positive phase, you had positive precipitation, convective heating anomalies over the tropical Pacific, and that produced teleconnections that affected climate over large areas, at least of the Pacific Rim countries, with dry conditions over South Asia, dry conditions over eastern parts of Australia, wet conditions over the southwestern parts of North America, and that these teleconnections coming out of anomalous atmospheric Rossby waves from the convective heat anomalies would drive anomalous low pressure in the North and South Pacific, and that would affect the strength of the trade winds, which would then trigger ocean Rossby waves that would start coming across very slowly because they'd be, say, at 15 to 20 degrees north and south. And that would then provide the slow time scale for this, the IPO that would then be reversed when the IPO was in its negative phase. So this is not to go into detail on this particular mechanism because we'll be talking about elements of this, but just to illustrate the fact that it has been hypothesized that tropical mid-latitude interaction and definitely coupled air sea interaction would be central elements of such a mechanism. Okay, so let's start by looking at some results from the DPLE, the Decadal Prediction Large Ensemble. And this has been analyzed quite a bit lately. These are large ensembles of initialized hindcasts, and the initial states are derived from something called a FOSSI, forced ocean sea ice technique, where you take observed forcing from the atmosphere and you force the ocean model with the ocean sea ice with that observed forcing from the atmosphere. And you do that, you run that through the 20th and early 21st century, and then you start again the early 20th century, run it through with the same time sequence of atmospheric forcing, and you do that 5 times, and the 5th time you do it, you presume that the forcing from the atmosphere has kind of been imprinted, at least on the upper part of the ocean, and then you can use those ocean states as initial states for initialized hindcasts. So when we started looking at this, at some of the heat content anomalies in these ocean initial states, we saw this kind of interesting characteristic that if you took this kind of off-equatorial box in the off-equatorial Western Pacific, north of the equator, and an off-equatorial box south of the equator, and average the ocean heat content above the depth of the 20 degrees C isotherm, of course, you see this interannual variability going on, but you also see this kind of interesting low frequency variability, such that around here in the 70s, it looked like that both the north and the south box, the trend was toward decreasing ocean heat content in both these boxes. And then here sometime in the late 90s, we started an increase in heat content in both of these boxes. And then here around the time of this 2015-2016 El Nino, it seemed to drop again. And not coincidentally, the turnarounds of these trends and kind of low frequency variability happen to correspond to transitions in the IPO. This negative to positive trend here in the 70s, positive to negative trend here in the late 90s, and negative to positive here around in the mid 20-teens. And so the other thing that was kind of curious about this is that if you look at Eastern Equatorial Pacific Ocean heat, or the heat content at the depth of the 18 degrees C isotherm, in other words, above the depth of the 18 degrees C isotherm, this 76, 77 El Nino event seemed to correspond with the time that this heat content in the Western off-equatorial Pacific seemed to start decreasing. The big 2-year 98 to 2000 La Nina event seemed to correspond with the time period when the heat content started increasing in the off-equatorial Western Pacific, and the big 2015 to 2016 El Nino event was right around the time that the heat content in both these off-equatorial boxes started to decrease. So this presented the interesting possibility that maybe there was some relationship between these interannual events and these kind of lower frequency changes in heat content in the off-equatorial Western Pacific and in these kind of changes in sign of the IPO happening on decadal timescales. But that was just from the DPLE, the initialized ocean state. So you're kind of in model world there. That's could be an artifact of the ocean model or something to do with the atmospheric forcing. So what if we looked at something that was more related to observations, at least related observations, because these are 3 ocean reanalysis products that assimilate available ocean observations. And of course, there's issues with these ocean reanalyses that they're not exactly observations, but Yin et al. Looked at this in 2018 from 3 of the reanalysis products and looked at a large box in the Western Tropical Pacific, 120 east to 180 east, 20 south to 20 north, which encompasses some of the areas we were looking at. And they saw similar kinds of things. So you saw this kind of buildup apparently on these kind of low, long time scales up until the 70s, kind of a drop off until the late 90s, an increase again in the 2000s, and then a drop off after the 2015, 2016 El Nino events. The timing of these low frequency changes in ocean heat content in the Western Pacific is very similar to what was seen in the initialized ocean hindcast states for the DPLE. So at least it looks like there is some aspect of this low frequency variability of ocean heat content in the Western Pacific that does have this characteristic that seems to relate in some way to these transitions of the IPO. This one going from negative to positive IPO, positive to negative IPO here in the late 90s, and negative to positive IPO in the 2014 to 2016 kind of time frame. So this leads us to propose a hypothesis involving this timescale interaction, that interannual timescale INSO activity occurring when a decadal timescale buildup of off-equatorial Western Pacific Ocean heat content has reached a necessary threshold. So there's this idea that there's this threshold that has to be reached that's necessary but not necessarily sufficient for a transition. But then a well-timed either El Nino or La Nina event can then contribute to a transition of the sign of the IPO from positive to negative or negative to positive. And this kind of arose as an analog to what's been proposed for subseasonal westerly wind burst events in the equatorial Western Pacific, contributing to a transition to an interannual El Nino event. So this is now timescale interaction between the subseasonal and interannual timescale. What we're hypothesizing is interannual timescale activity interacting with decadal timescale variability. And of course, the reason we're interested in this is we want to understand the processes and mechanisms to identify sources of decadal timescale variability. Let's see here. All right, so that's our hypothesis. We're going to analyze the 1800-year CSM1 pre-industrial control run. So this is an unforced simulation. So the first EOF of low-pass filtered SSTs is the IPO. And we know that this has some relation to observations from papers by Henley et al. And John Fasulo, where they've shown that these models can produce something that looks at least like something we think is the IPO that's in the observations. And that's the IPO index then is going to be the first EOF of low-pass filtered SSTs, the PC time series of the first EOF of low-pass filtered SSTs for the Pacific Basin. And then we're going to look at this index, this PC time series, to look at the transitions of the IPO from positive to negative, which is what we saw in the late 90s, and from negative to positive, which is what we saw in the previous plots in the mid 70s in the 2014 to 2016 timeframe. We get roughly 50 samples of each, 47 from negative to positive, 51 positive to negative. And we're going to composite the conditions associated with these transitions. And for most of these, the rest of the talk is going to be showing negative to positive transitions, but the positive and negative are going to be very similar, but with opposite sign. But to start out, I'm going to just say something about the distribution of El Nino events versus IPO transitions. This is just a scatter plot of Nino 3.4 SSTs and IPO, the IPO index. These are monthly values. And if you thought there was groupings of either amplitude or frequency, it doesn't really show up in this kind of a scatter plot. This is pretty random, but you do see large amplitude El Nino events and large amplitude La Nina events right around the times of the IPO transition. So the fact that this could be amplitude modulation or possibly just random groupings doesn't seem to be the case, at least in this model. Okay, I'm going to show one plot where I'm going to show both negative to positive and positive to negative, just to give you an idea of what this kind of looks like. Here in the top two panels, the top left here, negative to positive IPO. The blue line is the IPO index composited across these roughly 50 events. The blue dots here that are on this line indicate significance at the 95% level, that this is significantly different from the positive to negative IPO transitions. And of course, we're keying everything right around the zero crossing time. So we look at these boxes of heat content, the Alpha Equatorial Western Pacific Ocean heat content boxes. The north box is the green line, the south box is the red line. You can see it's kind of building up a little bit here. It reaches this kind of level here of about a half a standard deviation. These are all standardized units here. And then when the transition occurs, then this starts to drop off. And this is kind of what we saw in those previous plots from the DPLE and from the ocean reanalyses, that there's something about when this transition occurs and you have this kind of necessary threshold, the transition occurs and then you start to see a drop off of the ocean heat content in the Western Pacific. Similar to for positive to negative IPO transitions. Now this is the IPO index. We're keying around this zero crossing line here. And you see below normal values of Alpha Equatorial Western Pacific Ocean heat content here of about a half a standard deviation, that then the transition occurs and then it starts to increase. And so that again has similar characteristics to what we saw in the DPLE ocean initial states and in the ocean reanalyses data. So the question is there something about this transition that's connected to ENSO activity? So if you actually do a count of El Nino and La Nina events, this is defined, this definition here, this is April to March, 3.4 SSTs greater than a half a degree C for 5 consecutive overlapping 3-month seasons. And indeed, you see a greater chance of El Nino events occurring at this year 0, which is this at the crossing point here, about a 40% greater chance than La Nina events. And similarly, for the positive and negative transitions, you're seeing a greater chance of La Nina events compared to El Nino events, maybe about 50% greater chance. The units here are events per transition. And so these values are for the La Nina events are approaching 0.5, about 0.43 or so for the El Nino, for the transitions from negative to positive. So there does seem to be that there is a greater chance for El Nino for occurring at the time of an IPO transition negative to positive, and La Nina from positive to negative. So that is evidence that you're shifting the odds toward a greater chance of that thing kind of happening. But that's just for year 0. What happens for the years previous and following? This is just showing for the negative to positive, and positive to negative is very similar but opposite sign. This is the year 0, which we just showed. We just looked at that, showing the greater chance of El Nino events. But after the transition occurs, there's the base state appears to have changed such that there's a greater chance for El Nino events to occur after the transition occurs, not so much before the transition occurs. So this idea that something happens right around the time that the IPO transitions and the base state changes, it's more favorable for the occurrence of El Nino events to follow such a transition. It's always kind of difficult to wrap your head around this timescale interaction when you're looking at these low-pass filtered indices for something like the IPO, and how this relates to what's actually happening on interannual timescales. So in other words, if you're trying to compute some kind of low-pass filtered index, you're going to be dropping off years that you're currently experiencing because of low-pass filtering. So Ben Henley in a 2015 paper came up with another way of coming up with an IPO index. He called it the IPO tripole index, or TPI. And he just basically recognized that this pattern that we've seen before, this IPO pattern, you can actually average sea surface temperatures over these 3 areas. So if you average the sea surface temperatures over this tropical Pacific box and subtracted half the amplitude of the sum of these 2 Alpha Equatorial boxes here, you can come up with something that looks a lot like these other EOF-based indices, and you can actually plot this month to month. And so this is an interesting illustration from his 2017 paper where he shows the relationship between this monthly TPI index, and of course you're seeing a lot of interannual variabilities going up and down, and the low-pass filtered version of it, which looks more like the EOF low-pass filtered EOF PC time series that we've been using to study these IPO transitions. But there's a couple takeaways from this kind of a plot. One is the fact that these transitions, now this transition occurs here in this low pass filter index a little bit after this fairly rapid in a change in the TPI that occurs very rapidly within a year. And again, this transition going from positive to negative TPI or IPO occurs really rapidly. This real big drop in the TPI where it goes from positive to negative. And so these rapid drops are what's represented by this interannual timescale variability. But you still have interannual timescale variability superimposed on this kind of positive, mostly positive state. But after the transition, then you have mostly negative variability of the TPI, mostly negative values of the TPI, even though there's still real big interannual variability. So this is kind of what we're trying to deal with and understanding how this timescale interaction occurs. So when you get these low frequency or kind of decadal timescale transitions, you still have this interannual timescale variability occurring on top of it, but you're staying mostly above zero in terms of anomalies on these decadal timescales and mostly below zero for negative values of this index after the transitions, but there's still huge interannual variability going on. So I think that's a really nice way of illustrating this timescale interaction that we're trying to look at. So just to look at this again, these two timescales from the model, this is just now taking a couple of cases from the model. This is a case, and these are looking at annual mean values from the Nino 3.4 area, which are the colored values here. These ocean heat content boxes in the off equatorial Western Pacific. Then the north box is the dashed line, the south box is the kind of solid line. And you can see that this is, of course, the low pass filtered, the PC time series version of the EOF or of the EOF based IPO index. And so this is a transition going from positive to negative. And you'd expect in the composite sense anyway, that there'd be a better chance of a La Nina happening right around the time of this transition. And for this case, it does happen. You can see that the off equatorial heat content is below normal. It's kind of reached some kind of threshold value apparently here. And after the transition occurs, it starts to increase, at least for the north box. The south box, it starts to increase and goes below normal. And actually, if you looked at the next few years here, it does come back above normal. And so that's kind of what you're looking at when you look at a specific case. So you're seeing this interannual timescale variability. You're seeing that there's a La Nina event that occurs when the low frequency part of it transitions, and that does seem to be associated with some change in this off equatorial heat content in the Western Pacific. If you're looking at an example of a negative to positive transition, again, this is, you expect to see in the composite sense anyway, a better chance for an El Nino event to occur sometime around this transition. This is what's happening here. And then a better chance of an El Nino event kind of following it, which is what's happening here as well. The north and south boxes are kind of above normal here until the transition, then they start reducing. The south box in particular seems to be showing better behavior in terms of what the composite signal is. The north box decreases for a while, it comes up, and then it goes negative. And if you look for the next few years after this, it would actually be negative. So this is kind of what you're trying to understand is this timescale interaction where you got things happening on different timescales. We're looking at composites, which make it clear, but when you're looking at individual cases, you really have to be careful about how you interpret what's going on. So I'm going to go back to the composites to help us interpret what's going on, at least in a composite sense, to give us some idea of what could actually be happening and how it could be happening. So these are going to be a series of plots which are composites of starting here in the upper left-hand corner, 4 years before a transition. These are all going to be negative to positive. And as I said before, the positive to negative IPO transitions are going to look very similar to this, but with the signs reversed. In this case, we had 47 cases, so we were able to compute some statistical significance here. 5% level, that's the stippling that's in these plots. This is for sea surface temperatures. The boxes, the heat content boxes, we put on all these plots just for reference because this is what we're looking at. The center of action kind of in the Western Pacific. Going for 4 years before the transition, 3 years before, 2 years before, 1 year before. In the middle of this plot is the year of the transition in this composite sense. 1 year after, 2 years after, 3 years after, 4 years after. So we're going from upper left to lower right in terms of the time sequence of these composite transitions from 4 years before to 4 years after. So if you're just looking at sea surface temperatures, you see this kind of really nice negative IPO pattern here. You see bigger amplitude values of the sea surface temperature anomalies in this IPO pattern in the off equatorial Eastern Tropical Pacific. And this is a fairly well-known feature of this pattern, that you get the bigger amplitude SST anomalies off equator on these decadal timescales. And this pattern goes, you get these negative SST anomalies go all the way across the Pacific, right across the Pacific. whereas El Nino signals usually end somewhere around the date line, and they're much more narrowly confined to the equator. So this is kind of what you'd expect to see for a negative IPO pattern with these opposite sign SST anomalies to the northwest and southwest in the Pacific. This pattern kind of builds up, starts to switch. Now at the time of the transition, we go from these negative SST anomalies to all of a sudden we're getting positive SST anomalies all the way across the Pacific, and especially larger amplitude SST anomalies in the western equatorial Pacific. So this would be indicative of the fact that we're probably getting some westerly wind anomalies over here. We're getting Kelvin waves that are shooting across the Pacific to deepen the thermocline and contributing to these warming of SSTs in the eastern equatorial Pacific. So now the pattern is shifted, and we're getting this pattern that's opposite to what we saw before the transition. Now we're in a positive phase of the IPO. Again, we're getting these bigger off-equatorial lobes of SST anomalies in the eastern tropical Pacific, with biggest equatorial western Pacific anomalies here, all the way over here in the western Pacific and the date line and to the west. And so those are the characteristics of the time evolution of the SSTs, and we're going to try to relate what's going on in other quantities to what's going on with these SSTs. Now this is looking at precipitation anomalies. Again, this is going from negative to positive transitions, 4 years before to 4 years after, and the transition is right here in the middle. And recall, for the negative phase of the IPO, to expect to see negative precipitation anomalies, which you do see. These blue colors are negative precipitation anomalies. We see a little bit of a northward shift of the ITCZ, which gives us these positive anomalies here along the ITCZ, but mostly in this kind of big wedge-shaped pattern that we saw, it's characteristic of the negative phase of the IPO. You see below normal precipitation anomalies, and the biggest amplitude negative precipitation anomalies are over here in the western equatorial Pacific, which is an important part of this story that we're going to be looking at. Again, when we come to the transition, recall that at the time of the transition, we're getting positive SSTs across the whole Pacific, and now we're getting fairly large amplitude positive precipitation anomalies here in the far western equatorial Pacific, and those build up until we get this kind of these off-equatorial maxima positive precipitation anomalies associated with the positive SST anomalies. Now we get a kind of a southward shift to the ITCZ, so we get negative precipitation anomalies along the ITCZ. But the biggest positive values of precipitation anomalies are way over here in the western equatorial Pacific. And this kind of comes back again. This is kind of the center of action on these decadal timescales to what's going on that seems to be able to drive things that are happening elsewhere in the Pacific Basin. What this looks like in terms of sea level pressure and surface wind stress anomalies, when we get the negative phase of the IPO, you tend to get positive or anticyclonic circulations in the North and South Pacific. And you see these real big, long, dark arrows here. These are really strong trade winds. So the southeast trades and the northeast trades are really a lot stronger during the negative phase of the IPO, associated with these positive or cyclonic circulations in the North and South Pacific. And these stronger trades extend all the way across the Pacific, all the way to the Western Pacific and even into the maritime continent. During the time of the transition, you're starting to see these westerly anomaly winds in the equatorial Pacific that were associated with the transition of the SST anomalies from negative to positive. And you're also seeing a deepening of the lows in the North and South Pacific, which continue to deepen. Now we're having weakened northeast trades and southeast trades, and weakened surface trade winds in the equatorial Western Pacific, extending on to about maybe 160 east. But again, a lot of this is going on in the off-equatorial regions, the Eastern Pacific and the equatorial Western Pacific. So those seem to be the two areas that are kind of the most active. So now if we start getting into the kind of dynamics behind this, we can look at the U component or east-west component of the surface wind stress. We call this tau X. The blue colors are negative values or stronger easterly component surface wind stresses. The orange colors are anomalous westerly values of this tau X quantity. And I put in some black arrows here just to highlight the direction of the sign of the anomaly. So what's happening in the Western Equatorial Pacific, you're getting these stronger trades going all the way across here to Papua New Guinea and the maritime continent. But you're getting this kind of band of westerly anomaly winds around 15 to 20 north and 20 south. And those kind of hang in there until you get the transition occurs. And then now it goes to the opposite sign. Now we're getting these westerly anomaly winds, the positive values of surface wind stress in the equatorial Western Pacific, and also these weakened trades, these westerly anomaly trades in the off-equatorial parts of the Eastern Tropical Pacific, and these stronger easterly surface wind stresses in the off-equatorial parts of the Western Pacific around 15 north and 15 south. But of course, it's the dynamic response to the wind stresses that we're interested in. This is now the curl of the wind stress, which gives you an idea of what the vertical motions are being induced, or what vertical motions are being induced in the ocean, the upper layers of the ocean from these wind stresses. And this is just a cheat sheet down here for the sign of these things. So in the northern hemisphere, a negative value of curl of the wind stress, which are the blue colors, is Ekman pumping, which means you're pumping water downward. And the southern hemisphere, of course, has the opposite sign. So for Ekman pumping in the southern hemisphere, you have positive or red colors. Both these are giving you Ekman pumping downward. But again, just to highlight, these black lines, dark black lines, are showing the anomalous wind stresses. And now you can see that the Ekman, there's convergence to the Ekman transport to the right here from this in the northern hemisphere. So you're getting upward motion here, kind of right underneath the positive wind stress. Convergence of heat in the kind of around the 15 north and 15 south areas, just due to these response of the wind stress and the wind stress curl to the forcing. After the transition, everything's opposite. Now you're getting these easterly anomaly wind stresses from the previous plot that I highlighted here as a black arrow. Westerly anomaly winds in the equatorial Pacific. This is producing Ekman. Basically divergence, Ekman transport to the north, away from these values here, and convergence into the equatorial tropics. And when you look further to the east, if you look, when you have these period of really strong trades, you're getting divergence of heat out of the tropical off-equatorial tropics, and it's sending heat downward, and this would induce downward or downwelling ocean Rossby waves in this area here that slowly start coming across the Pacific and contribute to this buildup of heat content in the western off-equatorial Pacific. And the divergence of heat out of the deeper tropics is contributing to those kind of maxima of negative SSTs in these lobes that kind of extend out into this kind of wedge-shaped pattern in the southeast and northeast tropical Pacific. So what does this look like in terms of the actual heat content? So this is looking at heat content measured as just the depth of the 20-degree C isotherm. And as you can imagine, with these strong trades and this convergence of heat into the off-equatorial regions here, you're getting these positive values. And I've kind of highlighted where these positive values are in these off-equatorial regions. And of course, you're also getting heat content buildup just from the stronger trades here, just in the equatorial Western Pacific. Here in the off-equatorial Eastern Pacific, this kind of divergence of heat out of the deeper tropics is causing some heat convergence into the areas that are responding to that Ekman pumping going on in response to those stronger wind stresses. And after the transition, if you look down here in the lower right, it's just the opposite. So now we're getting these depleted amounts of ocean heat content in the off-equatorial regions and also the equatorial regions of the Western equatorial Pacific. Same thing. We have these basically a convergence of heat due to the Ekman transports to the weaker or westerly anomaly trade winds here in these kind of off-equatorial lobes that are produce these bigger values of SST anomalies in these off-equatorial regions of the Southwest Northwest Pacific. And you are probably thinking to yourself that this kind of looks kind of like the Pacific Meridional mode kinds of things. I'm going to talk about that a little bit more as we go along. But the center of action seems to be going on in the Western tropical Pacific. So what's actually going on there that we can ascribe to how these things are maintained? If we look at, this is just a kind of a snapshot zooming in on this 4 years before the transition from negative to positive. And recall, this is when we had the really strong trade winds, these negative values here. We had these westerly anomaly surface wind stresses here, and kind of the 15 to 20 regions to the north and south. And of course, this looks mysteriously, not mysteriously, but suspiciously like a gill response to some kind of convective heating anomaly down here. So you get these anticyclonic circulations to the northwest and the southwest of what would be a negative convective heating anomaly from those negative precipitation and negative SST anomalies here in the Western equatorial Pacific. So to check that out, we actually looked at a specified convective heating anomaly experiment where we just had the atmospheric model with observed SSTs, climatologic SSTs. We put a negative convective heating anomaly here at 165 East, which is roughly where there's a big center of convective heating anomaly where those very large negative precip anomalies were. And you get the same kind of response. You get this kind of gill type response with these anticyclonic circulations here to the northwest and to the southwest. And that then is contributing to these off-equatorial westerly anomaly surface wind stresses that's then contributing to the convergence of heat. So now, of course, this is in a composite and in an idealized framework. What's actually happening is, of course, there's El Nino and La Nina events that are interfering with this, but this pattern occurs enough of the time that, it occurs enough of the time that the ocean heat convergence is converging heat into these areas in the off-equatorial Western Pacific to give you that sustained kind of buildup, even though it's kind of being tapped into when there's an El Nino or La Nina event on the international time scale. Over time, it builds up such that it gets to this kind of threshold such that when you get an El Nino event that comes across, it's enough to discharge this heat into the equatorial tropics in the Western Pacific. Now, I mentioned before this kind of interesting Pacific meridional mode and South Pacific meridional mode like pattern. And for those of you who follow this literature, this kind of looks like what the Pacific meridional mode would look like. It kind of has this diagonal kind of signature. It's thought that this could actually end up propagating anomalies down into the Western Pacific. But the driver of this is thought, at least in the literature, to be kind of random or stochastic forcing coming across from the mid-latitude systems. Same thing for the South Pacific meridional mode. And in the literature, the South Pacific meridional mode actually sets up a little bit further to the east. So we're calling these PMM and SPMM-like patterns. They seem to be have a similar SST signature at least, but they're being driven, it looks like they're being driven, at least in the model, by convective heating anomalies that are in the kind of Western Central Pacific. So if you do a regression of this negative precipitation anomaly here in these composites from the 165 west and the equator, and regress that against sea level pressure, you see you get this big anomalous high or anicyclonic circulation in the North and South Pacific. And of course, the geostrophic part of that would produce stronger trade winds, which would be these kind of black lines that I've highlighted in here. And that then sets in motion all these dynamical coupled processes with wind stress curl, ocean divergence out of the, or heat divergence out of this area, where this lobe is, and give you cooler SSTs there. The fact that this could be actually being driven by convective heat anomalies. This is a convective heat anomaly experiment with the atmosphere only, where we put a negative convective heat anomaly at 135 west, which is a little bit further east, but it gives you the same kind of idea. You get these anomalous anicyclonic circulations in the North and South Pacific with these stronger trade winds in these off-equatorial regions being driven by these teleconnections coming out of the tropics. So we say these are PMM and SPMM-like because they seem to have a connection to convective heat anomalies in the tropics. And of course, then the winds with this would force ocean Rossby waves that could contribute to the buildup of heat content in the Western Pacific as they propagate across. So just to kind of summarize this, if it's possible, I'm going to just go through and try to review a little bit of this by showing conditions 3 years before a transition. This is now, the colors here are wind stress curl, to give an idea of the kind of ocean dynamics part of it being forced from the atmosphere. This blue circle is kind of just schematically illustrating the fact that's negative precipitation and convective heat anomalies that are in the Western tropical Pacific. The big black lines are where you get the wind stress, actual wind stress anomalies. So you get these westerly anomaly wind stresses, about 15 to 20 north and south, and these stronger trade winds here. So you get the strong wind stresses in the off-equatorial Eastern tropical Pacific. You get this kind of gill type response over here with anomalous anicyclonic circulations to the northwest and southwest of this negative convective heating anomaly. And you're getting these anomalous highs in the North and South Pacific, at least partly in response to the negative convective heat anomalies that are kind of in the eastern part of these precipitation anomalies that are driving these stronger trade winds, which then give you these the wind stress curl responses that produce this kind of these lobes of more strongly negative SST anomalies that are part of this kind of wedge-shaped negative IPO pattern that extends all the way across the Pacific to give you this kind of center of action that's going on in the tropical Western Pacific. If you look at the time of the transition, now this is the time when you see the SSTs across the Pacific warm up. There's evidence that this could be a better chance of an El Nino event occurring, and with bigger amplitude anomalies over here in the Western tropical Pacific. And that then gives you this positive convective heat anomalies, which is this kind of red, signified by this red oval, and some heat convergence coming out from the wind stress curl into the tropical Western Pacific. which would start to discharge this heat that's been built up in the off-equatorial Western Pacific. And then 3 years afterwards, now you get the opposite pattern to what we had 3 years beforehand. Now we get these westerly wind anomalies in the Western tropical Pacific, easterly anomalies, this gilt response now with the positive convective heating anomalies. So now you get anomalous cyclonic circulations to northwest and southwest, which contribute to these easterly anomaly wind stresses, which then are contributing to this kind of divergence of heat out of this kind of box centered around 15 north and 15 south, that then depletes this heat content and contributes to the maintenance of this kind of positive IPO pattern. So just to summarize this, I was trying to show that a transition from negative to positive can come about by the buildup of off-equatorial Western Pacific Ocean heat content anomalies. And these are maintained by these negative SST precipitation convective heat anomalies near 165 east and the equator, and with contributions from these PMM and SPMM-like processes farther east with the ocean Rossby waves that can come across and contribute to the buildup of heat content. Then it appears that there's a better chance of El Nino activity occurring that can contribute to a transition to positive IPO if these heat content anomalies in the off-equatorial Western Pacific are necessarily large. In other words, they've reached some necessary threshold, but not sufficient for a transition. The sufficient part of it comes in with El Nino activity to interact with this interannual timescale with the decadal timescale, and the onset of equatorial westerly wind anomalies, warm SSTs, positive precipitation, convective heat anomalies near 165 east in the Western Pacific. And this is, in some ways, you could argue, is analogous to a subseasonal westerly wind burst event in the equatorial Western Pacific, usually associated with an MJO event, contributing to a transition to an interannual El Nino event. So it's kind of the same idea of this timescale interaction, that a shorter timescale can contribute to changes of things on longer timescales. And then this positive phase of the IPO is maintained until these heat content anomalies in the Western Pacific are built up again. They become necessarily negative, and then La Nina activity could contribute to a transition to negative IPO with just the opposite set of processes, and then for the transition from negative to positive IPO. So thanks a lot.
Thanks, Jerry. We have plenty of time for questions, so you can either raise your hand under the reactions button in Zoom and ask your question out loud, or you can type your question in the chat. We already have a couple of questions in the chat that came in during the talk, so I'm going to start with those. Alan Robach asked, haven't Mike Mann and colleagues recently shown that the AMO is forced by volcanic eruptions and thus not predictable?
Yeah, I don't want to get into the AMO. I want to stick to the Pacific Basin. I think that's still an active area of debate. I think, and we have people at NCAR in the ocean section that could probably answer that better than I could. But yes, I think Mike in his paper was arguing that it probably is, or could be a lot in large part due to forcing from volcanic aerosols. But I think, and there's also some papers, Doug Smith had a paper that suggested that aerosol forcing from East Asia could actually contribute to IPO transitions. So I think that's still open for debate. I think for the evidence that we're presenting here for the Pacific, we're trying to make the case that it does look like there are some internal mechanisms that can produce this internal variability, that if we could initialize those conditions in the initial state for an initialized prediction, you may be able to get these processes going in the right direction to give you some skill just from the internal variability being predicted out beyond 1 or 2 years.
Okay, great. There's a question from Martha on the low pass filtering used for the IPO index. If it is decadal, I don't understand how the -4 to +4 time lags are so different. Aishu responded with the specifics about the filter, but I didn't know if you wanted to add anything there.
Yeah, I don't think I understand the question, because the conditions, as you go from the -4, and these are composites, of course, so they're pretty smoothed out, but the conditions, say 4 years before a transition to 4 years after, are pretty much opposite. I mean, there's some small differences, but the evolution in terms of the composites are pretty symmetrical. So, I mean, there's some differences, but I think, in a composite, you're never going to catch everything. And I think that the idea of using the composites was to illustrate what areas are important, what processes can be important. And I think one of the take-home things is really from these decadal timescales, the center of action is really in the far western tropical Pacific in a number of different, and for a number of different reasons.
Yeah, let me just add some follow-up from Martha. I just saw an additional chat. So if there are significant changes near the zero transition, 4 years is small compared to the filtering timescale, then does this mean that the transitions are rapid?
Yes, the transitions are rapid. And we're looking at 4 years before and 4 years after is kind of, if you're thinking that one cycle could be, 10 years, then we're looking at, kind of a big part of a cycle. Of course, they're not just 10 years, they're 10 to 20 years or even a little bit longer. So yeah, the transitions are rapid. That's the idea of that this interannual event can actually cause a transition that's fairly rapid. I was trying to illustrate that in that plot from Ben Henley's paper where he was showing the TPI index, monthly values of it, along with the smoothed or the low pass filtered version to show that the transitions in the TPI index can be pretty rapid if you're looking at monthly timescales that are then represented by this kind of low frequency, kind of a low pass filtered part of the index that is the one that's most familiar. But I think it's this idea of this, what it looks like on interannual timescales, what something like the IPO looks like on interannual timescales versus these decadal timescales, because on any given year, you're going to get these big El Nino and La Nina events happening. But kind of what's going on in the background are these more sustained kinds of things that can persist, that can survive from El Nino to La Nina event to give you this buildup of conditions that then can give you these thresholds that then can be triggered to produce a transition.
Great. There's a question from Chris. Does the meridional wind cross-equatorial component of the trades seem to play a role in the MM-like anomalies? I think MM is meridional mode.
Yeah.
Thinking about the WES feedback, maybe you or Chris can define that for us.
Yeah, wind evaporation, WES, what is it? It's basically a coupled atmosphere-ocean way of propagating anomalies down towards the tropics that's been proposed for the mechanism for the Pacific meridional mode and South Pacific meridional mode. And I think that could be actually happening here. I think the bigger signal for what we're saying is PMM and SPMM-like. These patterns are mainly, at least in the model, is being driven from the tropics with these convective heat anomalies. So it's not necessarily stochastic forcing from the mid-latitudes, which has been proposed for the PMM and the SPMM. So that's, and they're set up in a little bit different positions. And so they're similar in some ways, but I think the forcing, we have evidence that the forcing for this manifestation in this context is probably coming mostly from the tropics and from anomalous atmospheric Rossby waves. And then the wind stress anomalies associated with those teleconnections are then inducing this kind of these lobes that you see that have maximum SST anomalies, that kind of that diagonal character that is characteristic of the PMM and SPMM. This due to the wind forcing that is coming from the tropical mid-latitude interactions from the teleconnections. So that's kind of what the setup process we were setting up, and we didn't really look at the WES feedback as contributing to this because it seems like the bigger part of this, and the fact that it's set up pretty much all the way across the Pacific is at least in the model probably coming from tropical mid-latitude interaction.
Great. Chris says thanks. Other questions? We have time. I'll give folks a minute or two.
Apparently not.
Yeah, I'm not seeing anything, so I guess we can wrap up a little early. Thanks, Jerry, for a great talk.
Yeah, thanks, Katie, and thanks everyone.
Next week, we'll hear from Hilary Scannell from Columbia University. So hope to see you then. Thanks.
All right, thanks.